I'm Aurora Wild, and I am a student at Treasure Valley Math and Science Center in Boise, Idaho. This is the first of several astrophysics lessons aimed at helping beginners understand this cutting-edge physics field. I thought we would start today with something that we're all pretty familiar with: gravity. We may think of gravity as things falling down, and though this phenomena is due to gravity, there's a lot more happening here. Before Newton, there was astronomy, but Newton discovered and explained much of astronomy, creating a new field, astrophysics. If the classic story is correct, astrophysics was born when Newton saw an apple fall from a tree. Presumably, Newton was the first to ask why things fall, and to care enough to figure it out. He ended up proposing his famous theory of gravity that explains this phenomena. There was some understanding of this force before Newton, but his contributions were far more extensive than the preceding understanding. The theory says that all masses exert an attractive force on one another. This means that the Earth is pulling down on us, and we are pulling up on it. Based on Newton's third law of motion, we know that every force has an equal and opposite force that acts at the same time. These forces always act on two different objects. A force pair never acts on the same object because forces involve at least two things, and there must be a force in this pair on each of them. This means that the force that the Earth exerts on us has the same magnitude as the force we exert back on the Earth. For example, if I exert a force on this book, the book will exert the exact same force back on me. No matter if I exert a big force or a small force, the book will match the exact same force. This same concept happens with gravity. The Earth exerts a gravitational force on us, and we exert the exact same gravitational force back on it. Now, the reason that we fall to the Earth instead of the Earth just floating up to us is because we're significantly less massive. It would take a much smaller force to accelerate this paperclip than it would take to accelerate this car. I can exert the exact same force on both objects, and the paperclip will move and the car won't. This same phenomenon occurs with the gravity force that interacts between us and the Earth. People, or paperclips, are easier to accelerate, so we accelerate towards the Earth. Now, it's important to note that the Earth also accelerates. It just does so to a much smaller degree. This is because the mass of human civilization is such a small fraction of the mass of the Earth. So the acceleration of the Earth due to the gravity of people is negligible. Another thing that it can help to think about is a person jumping off of a boat. If you are in the middle of a lake and you jump off of a boat, you will move away from the boat. The boat will also move away from you. This happens because you exerted a force on the edge of the boat, and it exerted a force back on you. The force on you pushed you away from the boat. The force on the boat pushed it slightly in one direction. This visual may help you understand how the gravitational force acts in pairs. Newton created an equation that explained the gravitational interaction occurring between masses. The force invoked by gravity between two objects equals the gravitational constant, big G, times the mass of object 1 and the mass of object 2, divided by the distance between the two objects, represented by a small r squared. The gravitational force depends on four things: the gravitational constant, the mass of each object, and the distance between them squared. The bigger the masses involved are, the larger the forces are. This explains why the force that keeps you on the ground is so much stronger than the force between you and a paperclip. The further apart the masses are, the smaller the attractive force between them is. In the general relativity video, we will dive into why distance is squared in this equation. The important thing to note here is that this inverse relationship explains why the entire universe has not just collapsed into a giant ball of mass. Many of these masses are too far apart to exert a large enough force to accelerate them. If you imagine solar systems as magnets, that if they are all set far enough apart, they can exist as separate individual objects. They will not all come together as they might if they were set closer together. The force between these magnets must be balanced by forward motion of each magnet. Though the main force acting in this demonstration with magnets is not gravity, this demonstration may help you visualize how it can be possible that gravity has not caused the entire universe to just combine into one giant mass. The gravitational constant is a number that is true, as far as we know, for every gravitational interaction in the universe. The existence of this constant was predicted because of how weak gravity is compared to the other fundamental forces. There are four main interactions that act in the universe, and they are known as the fundamental interactions. These include strong force, weak force, gravitational force, and electromagnetic force. We say fundamental interactions rather than forces because forces come in pairs, according to Newton's third law, and are better discussed as interactions than just forces. Gravity is the weakest of all of them, so we need to multiply the entire gravitational equation by a super small number in order for the force to be comparable to other forces. Though the gravitational force is proportional to m1 times m2 over r squared, this equation will yield a number that is far too large in comparison to the forces these objects may experience due to the other fundamental forces. For example, if I had 2 bowls of ingredients for a recipe and I knew that one of them was 200 grams and the other was 0.75 pounds, I would need to convert one of the measurements so that I could have similar measurements. So for example, I could multiply the pounds measurement by 453 in order to get a measurement in grams of 340. Then I'll know how much is in each. This same thing applies to gravitation. We want gravitational force to be measured in newtons, since all of the other fundamental forces are measured in newtons. A newton is a unit of force in the metric system. 1 newton is the force that must be applied to a mass of 1 kilogram to accelerate it by 1 meter per second per second. We convert gravitational force to newtons by multiplying it by a very small number. It should be noted that this number is completely reliant on the units that we wish to express gravitational force in. If we wanted to express gravitational force in a different unit than newtons, then g would be a different value. That's all g is, a conversion factor. Newton knew we would need one, so he included it in the equation even though he didn't know what its value was. The actual magnitude of this constant was not found until about a century later in an experiment led by Henry Cavendish with a pair of lead masses. What we have here is a classic Cavendish experiment. There's a top bar, then a string, it's fishing line, so if it's tricky to see, that's why. Then it's all connected to this bottom bar. On either end of the bottom bar are masses. I used old doorknobs. Then, placed near the masses on the edge of the string, there's these cups full of cement. These masses will attract the masses at the edge of the bar, and because this pole faces virtually no friction other than tension in the string, it will move towards the cups. This is how Cavendish first went about finding the gravitational constant g. The results I got are shown here. The position of the bar was measured for several days, and the small masses rotated towards the cups. The reason for this result is the gravitational force between the masses on the balance and the cups. This is the equation Cavendish used. It is derived from the gravitational equation Newton proposed. G, of course, being the gravitational constant, L being the length of the bottom rod, R being the distance between the lead bricks and the masses, M being the mass of the lead bricks, and T being the torsion coefficient in the string, which just accounts for any force due to twisting the string. The result he got is within 1% of the standardly accepted value today. He got G equals 6.74 times 10 to the negative 11th. Today, we use 6.67408 times 10 to the negative 11th for G. This new value is because of increased precision and repetition of experiments. Once Newton had explained the falling of the apple, he took a controversial stance for the time. He thought that all cosmic movement was due to gravity. Now, this was very controversial because most people thought that all of the stars were just placed in a divinely prescribed path. They thought of gravity as the thing that makes things fall, and therefore understood his theory as though everything was going to come hurtling into the earth at breakneck speeds. What they didn't understand is that gravity isn't just the thing that makes things fall. Gravity is a force that attracts all masses. Newton thought that this force might explain all cosmic movement. He claimed that orbit could be explained by gravitation. I have a lanyard that's attached to a flash drive. If I swing it around in a circle, we can see that the flash drive continues to move in a circle around my hand. The lanyard pulls it towards my hand, but it's moving fast enough that it never actually hits my hand. Take the moon, for example. The Earth is pulling on it hard enough to keep it from just flying away, but it's moving fast enough that it never actually hits the Earth.
Another way to think about orbit is what I like to call the cannon analogy. Imagine there is a cannon pointed towards the horizon of Earth. As the ground extends in front of the cannon, the surface of the Earth curves. If you shoot something out of a cannon fast enough, it will never hit the surface of the Earth because the Earth curves away from the object before the object can hit it. The object still has gravity acting on it. It's just moving so fast that it never hits the ground. This is how we launch satellites. Today, we talked about Newton's third law of motion, Newton's law of gravity, the gravitational constant in his equation, and how gravity explains orbits. Huge thank you to Daniel Fleisch, Paul Verhaeg, and David Whitaker for helping me with this script.
In the next video in this series, we will delve into why gravitational force acts the way it does, also known as general relativity. Thank you for watching.